Now next and the last part of the chapter we are going to discuss, that is the fifth type of reaction, that is redox reaction. As I mentioned in the last class also, that redox reaction is nothing else but the combination of two different reactions. One is reduction and second is oxidation. So first of all, we will understand the literal meaning of reduction and oxidation, and then we will see how redox reactions takes place. So when we talk about oxidation and reduction, we need to understand the meaning of oxidation and reduction, and these two terms can be expressed in multiple different ways. So first way of expressing oxidation and reduction is in terms of oxygen transfer. So basically, oxidation, as the name suggests, or as it looks like, earlier, a long ago, when we had just discovered oxidation, we used to relate this term directly with oxygen or reaction with oxygen and all that. So basically, something in which we are going to deal with oxygen. That used to be the old story. Now, this is not the way how we will be learning oxidation and reduction, and that is now how we will be analyzing a reaction as redox reaction. But I'm just telling you that long ago, when the oxidation and reduction terms were coined, at that time, oxidation term was very much in sync with the addition of oxygen. So we have one definition of reduction and oxidation in terms of oxygen exchange also, or oxygen transfer also. So what is the first definition of reduction and oxidation? Oxidation means when you have, assume I have two substances, A, B, O. Okay, and the reaction is taking place and the product is forming AO plus B. Now look at this reaction very carefully. What I can say is A is species 1 or reactant 1. Okay, and BO is the reactant 2. So B means any element or species or ion, anything, and oxygen is the other thing which is attached with the B. Now when the reaction took place in any circumstances, the product form was AO and B. That means this oxygen went to A and formed a new bond, forming a new compound AO. AO means basically oxide of A, and B came out. So basically what happened, the transfer of oxygen happened from BO to A. Now A became AO and we got B over here. So this is the oxygen exchange, and this was the first way how we had learned reduction and oxidation in the earlier times. So whenever the oxygen is transferring from one position to another, basically for A, what is happening? Gain of oxygen is happening. It didn't have oxygen in the reactant state, but in the product state, it got oxygen, right? So this conversion of A to AO is called as oxidation. Basically, it got oxidized. Basically, it got oxygen in it. Okay, whereas the conversion of BO to B, basically BO left its oxygen or had given away its oxygen, or loss of oxygen happened in BO and it became B. This is called as reduction. This is one way of expressing oxidation and reduction reaction, and in this reaction both are happening. Oxidation is also happening as well as reduction is also happening. Okay, now similarly we can also talk about oxidation and reduction in terms of hydrogen transfer. So oxidation and reduction in terms of hydrogen transfer. So it's not necessary that we are always going to deal with only oxygen. There might be hydrogen present over there and we will be dealing with hydrogen. So now let's see what happens when we talk about hydrogen transfer. I'll take a generic reaction again. So let's say I have A and BH, and it got converted into AH plus B due to any circumstances. Now what I can see is, in this, what has happened? B had hydrogen in the reactant. Now in the product, loss of hydrogen has happened. So loss of hydrogen is happening. Whereas if I talk about A, after the reaction, gain of hydrogen is happening in A. Now here, in whichever reaction the loss of hydrogen is happening, loss of hydrogen, such reaction will be called as oxidation. So it is little opposite of what we have learned before. Here Gain of oxygen was called as oxidation. Here loss of hydrogen is called as oxidation. So oxidation can be either gain of oxygen or loss of hydrogen or both together, okay, depending upon the reaction. Similarly, gain of hydrogen is called as reduction. So according to one reaction, gain of oxygen is called as oxidation. According to the other reaction, loss of hydrogen is called as oxidation, and the vice versa in case of reduction. So these are two very basic definitions which we had understand when we started studying about oxidation and reduction. So loss of hydrogen, that means BH to when conversion from BH to B is happening, this will be called as oxidation, whereas conversion of A to H will be called as reduction. This is in terms of oxygen and hydrogen only. So that means when we talk about reactions where there is transfer of oxygen and hydrogen, only those reactions can be categorized into redox reactions or reduction and oxidation reactions? Totally no. This was the concept in the beginning when we had just learnt about the oxidation and reduction, but that doesn't mean that reduction oxidation doesn't happen in any other reaction where there is no oxygen or hydrogen is involved. Oxidation reduction can happen in any type of reactions. So now we will learn the actual way of understanding how the reduction or oxidation takes place and understanding it in little more macro level, basically in terms of electrons, gain of electron, loss of electron, and all that, how the electron transfer happens, and then the reaction is called as either reduction or oxidation. Now we will understand the reduction and oxidation in terms of electron transfer, and this is very important because most of the reactions you will have to analyze in this way only, because this is the right way to understand redox. Now when I say oxidation is loss of electron, that means if I have any element A and it loses electrons, that means it is getting oxidized. Whereas if I talk about any element which is gaining electron, that is called as reduction. Let's understand it through this. Let's say I have taken a reaction A plus BCl. Okay. And after the reaction, the compound has ACl plus B. Now, all of you, I hope, have heard about valencies of the elements, and you should be knowing it by now because I had shared a list also, and you have learned this in grade 9th also. We call valency as, in a better terms, that is called as oxidation state. Oxidation state is the another term what we can use for valency. And this basically represents the current state of an element, whether it's in the neutral form or it's in the ionic form, and what charge does it carry in the current state. Okay, so I'll be using this oxidation state as the term whenever we are talking about the charges on any element or any species or any ion or anything. Okay, now assume if we are talking about A right now, just try to understand it very, very carefully. Can we see any charge on A right now? No. The charge on A is 0. So I can say that the oxidation state of A is 0. Right? Whereas if I talk about BCl, okay, chlorine's valency, all of us know what chlorine exhibits. Chlorine exhibits -1, so we will assume it would be exhibiting -1 valency or -1 oxidation state over here. Whenever we are doing the reactions, you have to write it this way. Whenever you are trying to figure out reduction and oxidation, you have to mention these oxidation states on the elements or on the species. So chlorine, all of us know that shows -1 valency, or I can say it shows -1 oxidation state. Now overall the molecule doesn't have any charge, correct? So if it doesn't have any charge, that means x minus 1 is equal to 0, no charge on BCl, right? So what would be the valency of B, or what would be the oxidation state of B? X is equal to 1. I'm assume there is x valency over here. Little common sense, both would be of equal quantity, that is why there is no charge on the molecule, correct? So I have got it that my B has current oxidation state as +1 for B and -1 for Cl, correct? If you don't know the valency of anything or oxidation state of anything, that's how you calculate. So if you don't know for BCl, overall charge on BCl is 0. Chlorine's valency you already know, or oxidation state you already know, so that you will write -1. B's you consider X, so X plus -1 should be equal to 0. So your X will have 1 as a oxidation state or valency. So that's how you identify if you don't know. Correct? So now B has +1 charge, chlorine has -1 charge, or B has +1 oxidation state, Cl has -1 oxidation state, and A has 0 oxidation state. Now look, when the reaction has happened, what changes happened on A and B in terms of oxidation state? B, which was +1 over here, has become what? 0 over here. Oxidation state of B is 0 now. Right? Whereas if I talk about ACl, chlorine will still remain -1. Valence will not change. And A's oxidation state has become +1. Correct? So what is the observed change over here? A was 0 in the reactant side. Oxidation state was 0. And now it has become +1. How any species get a positive charge on itself? By losing the electron. So A must have lost 1 electron, and then it would have become A +1. Whereas if I talk about B, because the change has happened in B, not Cl, so we will not talk about Cl here. Now B had +1 charge or +1 oxidation state, and it has become B0. Basically 0 oxidation state. So how this +1 charge will get nullified? That means it would have absorbed or gained 1 electron, and that's how it has become 0. So that means gaining of 1 electron has happened over here. So I can see, if I look at the reaction very carefully, A in the reaction has lost an electron, whereas B in the reaction has gained an electron. Just now I had told you loss of electrons is called oxidation. So loss of electron, here what has happened is loss of electron. So this is your oxidation. We can call it one more way, that gain in positive charge. It had no positive charge right now, then it became positive over here. Or assume if something was negative, assume we had A as -2 valency or oxidation state, and it would have loosened 1 electron. That means it had 2 extra electrons, it had lost 1. So it would have become A -1. Right? So basically lowering of negative charge is also oxidation. So you can talk it in any way. You can just look at the loss and gain, or you can see the charges changing. Either way you can remember. So positive charge will increase and negative charge will decrease. That is what the oxidation is. Whereas if I talk about the reduction, the gain of electron happens. Gain. So in this what will happen? Your positive charge will decrease, whereas your negative charge will increase. So this way of analyzing a reaction is the right way of analyzing a reaction, and this way in the electron transfer, electron exchange, we call it redox. I have taken a sample reaction, a very random reaction. Now I'll take an example and I'll explain it through the exchange of hydrogen, exchange of oxygen, as well as exchange of electron. In terms of all these 3 terms, I'll be discussing some real-time examples of redox reactions. Now let's understand these reactions using all different definitions what we have learnt for reduction and oxidation. Now look at this zinc oxide. I have taken zinc oxide and it is reacting with carbon. Basically we are heating carbon and zinc oxide together, and in result we are getting zinc plus carbon monoxide. Just by simple observation, you can see that zinc was along with the oxygen earlier, and now that oxygen has been transferred to carbon in the product, and it has become carbon monoxide. So from zinc oxide to zinc, loss of oxygen is happening. Loss of oxygen. Whereas from carbon to carbon monoxide, gain of oxygen is happening. Gain of oxygen. So what we can say, loss of oxygen is what? Reduction. So what we can say, loss of oxygen is reduction. So zinc got reduced, or reduction happened for zinc, whereas carbon gained oxygen, and hence this will be called as oxidation. So in this reaction, from zinc oxide to zinc conversion is your reduction, and carbon to carbon monoxide is oxidation. This I had explained you with the help of oxygen. I can explain you the same thing with the help of electron transfer also. So let's try to see with the help of electron transfer. I had zinc oxide earlier. Oxygen's oxidation state is -2. So I will write -2 over here. overall zinc oxide has no charge over it. So zinc would be exhibiting +2 charge here, or you can say +2 oxidation state over here. I have already explained you how to calculate if you don't know what is the charge on an element. Then come to this. Then carbon. Carbon has no charge on it. It is 0 right now. So basically, elements in their elemental form will carry 0 oxidation state. For example, oxygen never stays as O. It always found as O2. So oxidation state of oxygen will be 0 in this case. Chlorine is always found as Cl2. So in its elemental state, it will always have oxidation state as 0. Hydrogen is found as H2. So the oxidation state of hydrogen here will be 0. When you talk about carbon, normally carbon is found in the nature as only C. So the element in this elemental state, the oxidation state on carbon will be 0. Iron as Fe, aluminium as Al. So in all these elemental form, your oxidation state of the respective element will be 0. But if they are in the combined form, as in the compound form, which have been formed after the reaction, then they will exhibit their specific valencies or oxidation states. So zinc here is exhibiting +2, oxygen is exhibiting as -2, carbon is 0 because it is in the elemental form right now. Now look what it is forming. It is forming zinc in its normal elemental form. Zinc exists as Zn in the normal elemental form, so it has 0 oxidation state, whereas carbon has become carbon monoxide. Now oxygen is -2 over here and carbon will be exhibiting +2. Correct? So now look at the change. Zinc, which was +2, had gained 2 electrons. Gaining of electron is called what? Gaining of electron is called reduction. Whereas carbon, which was 0 earlier, had become +2. That means it has lost 2 electrons. Loss of 2 electrons. Loss of electrons is oxidation. Oxidation state change happened? No. So there is no change with respect to oxygen, but zinc and carbon had their respective changes in terms of oxidation state, and through that also we can tell whether where the reduction is happening and where the oxidation is happening. So I could tell it using oxygen concept also, and I could tell it using the electron concept also. When you have oxygen transfer happening or exchange happening, then you can just look at it and you can directly tell the answer. But in many of the cases, we don't have oxygen even participating in the reaction or oxygen in the compounds to show whether the reduction is happening or oxidation is happening. At that time, you have to specifically use this method to understand. Now look at the next example. And next example, look at the copper very carefully. Copper oxide is there and then it has become copper. So loss of oxygen. So this is what? Reduction. Look at hydrogen here. Hydrogen has gained oxygen, so gain of oxygen. So oxidation. If I speak in terms of electrons, copper, I'll just write it over here. In copper oxide, oxygen was exhibiting -2 oxidation state, copper was exhibiting +2 oxidation state. Hydrogen is in its elemental form and hence it is showing 0 oxidation state. After the reaction has happened, copper has become 0 because it is now in its element state, the way how it exists in element. And hydrogen has become, oxygen is exhibiting -2 and hydrogen is exhibiting +1 over here. Right? How will you calculate? Oxygen is -2, 2 hydrogens are there, so write 2x plus 2x minus 2 is equal to 0. So x minus 1 is equal to 0, so x is equal to 1. So you can just simply calculate it. So what we can see, copper is gaining 2 electrons, whereas hydrogen is losing 1. Each hydrogen is losing 1 electron, and that's how the reaction is happening. Now gain of electron is reduction and loss of electron is oxidation. So we can relate both of these reactions in terms of electrons also and in terms of oxygen, hydrogen also. Let's see the last reaction, in which I have tried taking multiple different things so that we can relate everything. So what we can see over here is we have magnesium oxide and then it has become MnCl2. So basically loss of electron has happened. So I can fairly guess that this is reduction. And for HCl, hydrogen is gaining oxygen. So oxidation of hydrogen is happening. But what about chlorine over here? Something must be happening with the chlorine also, right? So I don't think we can get a clear information through this reaction just by using oxygen and hydrogen. Instead, I would prefer using an electron transfer method to understand where and how reduction and oxidation is happening. So let's see. Oxygen, there are two oxygens over here. Each oxygen exhibit -2 oxidation state. If I have two oxygens, both of it will be exhibiting -2, so total charge is -4. Assume we don't know manganese charge, so it is X plus 2 into -2, and overall charge is 0. So X minus 4 is equal to 0, so X is equal to 4. So now we got to know that manganese has +4 charge and oxygen has -2. Each oxygen has -2, so we have two oxygens over here. So each oxygen is -2 charge. So we'll be talking about single oxygen only. Chlorine is -1, hydrogen should be +1. Correct. Now come to the product side. There is chlorine. So let's figure out what is the manganese oxidation state over here. X assume. And we have two chlorines with -1 charge. Overall charge in the compound 0. X is equal to +2. So basically, manganese is exhibiting +2, whereas each chlorine is exhibiting -1 charge. So we are not multiplying the whole charge and writing it together. We are just writing a charge for single element. Okay, we are not writing for all the number of chlorines present over there or all the number of oxygens present over there. We will just write for element. We will not write for the group of elements. Okay, chlorine, it's in the elemental state. Charge on it is 0. Hydrogen is again +1. Oxygen is -2. So let's see where all the changes are exactly happening. Now, I'll just point out few important things which probably we had observed only through the initial observation. I said that HCl seems like hydrogen has got oxidized because it got oxygen over here. Look at it very carefully. Hydrogen had a +1 oxidation state over here and it is still maintaining +1 oxidation state. So is there any change in the oxidation state of hydrogen? Not at all. So that means no change has happened for hydrogen. Neither reduction has happened nor oxidation has happened. So that first thing was wrong. If I would have just observed it with the help of oxygen, then I would have got it wrong. Okay. Now second thing, look at the manganese. Manganese from +4 has become +2. From +4 to +2. So basically it has gained 2 electrons. Gaining of electrons is reduction. So MnO2 is getting reduced over here. So reduction is happening. So this is reduction. I hope it's not becoming very clumsy. I'm just rubbing the upper thing. I hope you would have noted it. So this is reduction. So basically, your MnO2 is getting reduced, or reduction is happening for MnO2 to convert itself into MnCl2. Now, look at oxygen. Oxygen is -2 over here and oxygen is still -2 over here. So no change in the oxygen also. Look at the hydrogen. Hydrogen is same. Now look at the chlorine part. So chlorine here is -1, whereas when it formed Cl2, it became 0. So that means from Cl minus 1, it has lost 1 electron and became ClO or Cl0. Loss of electron is happening, correct? The loss of electron is what? Oxidation. So from HCl, your Cl2 has become, from HCl, Cl minus 1, it has become Cl2 0. That means the HCl has got oxidized, or oxidation has happened to form Cl2, or you can also relate it as that chlorine had hydrogen earlier, it has loosened its hydrogen. The loss of hydrogen is also oxidation. So both way you can consider that HCl after oxidation has become Cl2. So from which to which oxidation is happening? From HCl to Cl2 oxidation is happening. From MnO2 to MnCl2 reduction is happening. So these are two very important things, and this is an important reaction to understand this. Now I'll tell you the two basic terminologies along with this reduction and oxidation. This is nearly everything with respect to reduction and oxidation. We have to understand two different terms. One is reducing agent and another is oxidizing agent. So what is agent? First of all of you should know at least the literal meaning of agent. Agent is the one which helps in doing in something, or which basically leads to a particular result. what we are expecting. Or if I say that I need an agent to find out a home, so basically the agent helps me in finding the home. So to take that process more smoothly, we require an agent. So agent is the one which causes the reaction to happen in case of chemistry. So when I say reducing agent, any substance which is causing reduction to happen, which is helping in reduction, will be called as reducing agent. How this reducing agent will help? Reducing agent will give whatever is necessary in reaction to do reduction. Okay? For example, if I have hydrogen, let's say, okay, and there is another substance A with me, and A wants to get reduced, I will give away my hydrogen to A, and A will get reduced. Right? So I am the agent, the one who has given hydrogen to A, so that A could do the reduction reaction. So agent do everything possible to make the reaction possible. Correct? So when I say reducing agent can either take away the oxygen or can give away the electron and can do all the dealing with respect to the electron. It will do to itself so that other substance can get reduced. Anything which is required for other substance to get reduced, it will do that. Okay, and similar is the case for oxidizing agent. Oxidizing agent will do everything possible to make sure that the other substance gets oxidized. Now just understand this. Zinc oxide wanted to do the reduction. It wanted to get reduced. It wanted to become Zn. If there wouldn't be a carbon over here, could zinc oxide become zinc? No. Was it possible for zinc oxide to become zinc? No. So which element helped zinc oxide to become zinc? Carbon helped. Okay. So in this case, because carbon was present and it could pull away the oxygen of zinc, zinc oxide could become zinc over here. And reduction was possible. So for reduction from zinc oxide to zinc, to let this reduction possible, carbon played its role by pulling the oxygen from zinc oxide, and hence carbon is your reducing agent. Carbon is your reducing agent over here, which helped zinc oxide to get reduced. And similar is the case for zinc oxide. Assume carbon wanted to become carbon monoxide. If let's say zinc oxide was not there, could this carbon become carbon monoxide? No. So because zinc oxide was present and it was ready to give away its oxygen, that's why carbon could become carbon monoxide. So what is the substance which helped carbon to become carbon monoxide? Zinc oxide. So zinc oxide is your oxidizing agent. Generally, you can just relate it this way also, that whichever molecules or whichever reactants are doing reduction, they are generally called as oxidizing agents also. We write it as OA. Reduction is happening for them. Basically, they are reducing themselves and oxidizing the another substance. And wherever the oxidation is happening, those reactants act as oxidizing agent. They are oxidizing themselves and reducing the other substances. So carbon will be acting as reducing agent over here. Similarly, look at copper oxide and hydrogen. Copper oxide had given away its oxygen to hydrogen so that it could form water and oxidation could take place. That is why this carbon monoxide, sorry, not carbon monoxide, I'm repeatedly saying it, carbon monoxide, copper oxide is your oxidizing agent because it helped hydrogen to get oxidized, whereas hydrogen took away oxygen, and that's how hydrogen helped copper oxide to become copper, or helped copper oxide to do the required reduction. So this is your reducing agent. So wherever oxidation is happening, those reactants will be considered as reducing agent. Wherever the reduction is happening, those reactants will be considered as oxidizing agent. That's how you have to remember it. Now look in the third case. Now MnO2, in case of MnO2, Mn has gained 2 electrons from the other substances so that it can get reduced. And how it could gain? It could gain because your chlorine was giving away the electron. So chlorine had given the necessary electrons to Mn to get reduced. So which chlorine? The chlorine which was present in HCl, and hence HCl will be called as reducing agent. whereas manganese has absorbed or gained the required electrons and made sure that chlorine could lose electron properly. Otherwise, the whole system will become unstable. And because it gained the electron, because it was ready to gain electron, chlorine could give away the electron and HCl could get converted into Cl2. And that is why your MnO2 will be called as MnO2 will be called as oxidizing agent. So you can just remember it this way: wherever the reduction is happening, those reactants will be called as oxidizing agent. Wherever oxidation is happening, those reactants will be called as reducing agent. Okay, so this is about reduction and oxidation. Now next we will understand what is the actual application of these reduction and oxidation reactions. By the way, I didn't tell you one thing, that is, what is the meaning of redox? Redox is the combination of reduction and oxidation. All the reactions have reduction and oxidation both happening in them, and 3 words of reduction and 2 words of oxidation combine to form redox reactions. And redox reactions are the ones where reduction and oxidation both happen simultaneously. Mind it, whenever we are talking about the redox reactions, they may fall into the category of other type of reactions also. For example, displacement reaction, double displacement reaction, or precipitation reaction, any reaction. So redox reactions can be the part of other category also. Okay, now let's talk about corrosion of metals. So just now we have understood what is reduction, what is oxidation, what does the reduction oxidation means in terms of oxygen, hydrogen, electrons, electronegative element, electropositive element, all basic understanding what we require to understand redox reaction or reduction or oxidation, we have already got it. Now we are discussing about 2 different applications of reduction and oxidation in our day-to-day life. And one of the most common and most visible, which all of you would have seen, is corrosion. So what is corrosion? I'm not very sure whether you have ever noticed or not, but at least for iron you must have noticed that if iron is kept for a longer time, any iron nails or anything, iron pieces have been kept somewhere, what you will find is that over a period of time they develop a brown color coating on them, and that is called as rusting. So basically they develop a brown color coating on themselves, and you must have also seen if the whole thing has got brown, basically if the whole iron piece has become brown, then it becomes quite brittle, as in like if you press it, it breaks down into smaller pieces. So this is when your iron articles get a brown coating on themselves and then become weaker, whereas iron piece cannot be broken through the hands. Forget about breaking it through the hand. You cannot even, I mean, at least me or anybody else, if you try to break it through hammer or anything like that, it's not so easy to break it. So basically rusting is making it quite weak. What exactly is happening in the rusting? What exactly is happening in the rusting? Rusting is nothing else but the same reduction and oxidation reaction what we have learnt just now, and this reduction and oxidation is happening on iron. So let's not specifically talk about rusting. Instead, let's talk about the corrosion. So corrosion is oxidation on any metal surface in the presence of oxygen, water, or any other acidic gases which are present in the atmosphere. When these gases attack on the metal surface and starts reacting with it, they basically form a different compound, which is an oxide of that metal. When they form the oxides or carbonates or sulfides or any such kind of compounds, basically the composition of the element also changes. Basically it was an element before and now it becomes a compound, and hence the properties will be different. That's what we have learned for the chemical reaction. In chemical reactions, what happens is the reactants have different properties, the products will have different properties. So when corrosion happens, your metal surface gets attacked by oxygen, water, or any acid gases present in the atmosphere, and then starts reacting with it. When it reacts with those gases, the metal gets converted into the respective compounds, and those compounds are weaker and many a times they have a different color as compared to the original metal, and the properties are also quite different. So we also call it eating away the metal by oxygen, water, or acidic gases. Why we are calling it eating away? Eating away means, so basically the metal which was a very stronger element before has become a weaker compound now. The properties have gone. You cannot use it in the exact same manner how we were using it earlier, and that is why we call it eating away. So oxygen, water, acidic gases reacting with the metal, making it weak, eating up the surface. So surface has become weaker, and then they go to the layer beneath and then start eating up that, and slowly the whole metal comes in contact with oxygen, water and acidic gases, and then becomes a different compound and becomes a weaker compound. This is your corrosion. Okay, so exactly that is what we have defined in the corrosion of metal also, the process in which metals are eaten up gradually by action of air, moisture or chemicals. Which chemicals? The acidic gases which are present in the atmosphere on their surface. This reaction takes its own sweet time. It doesn't happen immediately. It doesn't happen in the moment or an hour or 2 hours. It takes its own sweet time. So you will see that development very slowly. So basically, when we talk about corrosion, corrosion is not a matter of a day or two. It may take months. It may take years. So the reactions are relatively slower, and the metal gets converted into their respective oxides, carbonates, sulfides, and so on. So we will see few examples of corrosion. The first example is rusting of iron. As I had mentioned, you must have seen that brown coating on the iron. So what happens when you take an iron piece? This is your iron. It comes in contact with oxygen and oxygen and water together starts attacking on the iron surface. Basically, oxidize your iron. So these are the oxidizing agents and doing oxidation on iron. Okay, and water presence is required for oxygen to oxidize iron, and hence forming Fe2O3, that is iron oxide dot XH2O. What do we mean by dot XH2O? That means some content of water is also got trapped into it, or water vapors have got trapped into it, and we call it hydrated iron oxide. Due to this water trapping, this iron oxide becomes much more weaker, and this whole composition, this X means it can be any number of water molecules. We do not have a fixed proportion of it. So any random number of water molecules can come along with this Fe2O3, can be attached, and then the compound formed is hydrated iron oxide, which is a brown color compound, reddish brown, and this is called rust. And this is the one which can be broken, or which can be converted into pieces or powder just by crushing to it. And this is way weaker compound as compared to the iron. So all of us have seen rusting. If you have not seen, start observing around. When it is on just on the top layer, you may not find the difference in the strength of the iron piece, but as slowly the rusting will start happening for the inner layers also, the whole thing will become extremely weak and can be broken very easily. Similarly, look at the corrosion of copper. This is quite common. Corrosion of iron. Corrosion of copper, I'm not very sure how many of you would have seen, but as per my understanding, most of the people have copper vessels at home. So if you keep the copper vessel outside for a longer time, you will find a greenish layer on the top of the copper vessel, and you can just rub it through or scrub through it and it will clean. So what is that greenish layer? So copper comes in contact with the carbon dioxide in the atmosphere, oxygen and water. All these three slowly start attacking the top layer of the copper and convert it into copper carbonate and copper hydroxide both. So your copper gets converted into copper carbonate also, and copper gets converted into copper hydroxide also, and the combination of both is basically a green color substance, which we can see on the copper vessels, which can be rubbed and can be cleaned, but if you'll not clean it for a longer time, it will keep corroding inside the copper vessel also. Similarly, you must have seen the silver ornaments becoming black, or silver vessels, or silver any silver substances becoming black over a period of time. So why does that happen? That happens because silver, when comes in contact with H2S, that is hydrogen sulfide gas, which is generally present in the atmosphere. the hydrogen sulfide gas present in the atmosphere and oxygen which is present in the atmosphere, both starts attacking the silver. Silver is a very less reactive metal, so it takes its own sweet time to react, and then eventually it forms Ag2S, which is nothing else but silver sulfide. This is the formation of this Ag2S causes the formation of a black layer on the silver ornament, and the water particles gets released. So this is your black coating. You can rub this, you can rub it off, you can clean it off, and then you'll get your silver ornament again shiny. But mind it, when you're rubbing it, you are basically washing off the silver also. So top layer of silver is just washing away. Okay, so these are the different reactions of corrosion of different metals. In your NCRT, I think mostly they have spoken about only rusting of iron. We have discussed about the three elements so that you get a better idea how the corrosion happens and how it happens for the other metals also. Now we'll talk about how can we stop corrosion, or we can say how we can specifically stop the rusting of iron. So how can we protect our iron articles from rusting, or instead we talk about how can we prevent corrosion on any metal. So there are a few things. First is galvanization. What is galvanization? Galvanization is coating of zinc. Zinc prevents the metal below from rusting or oxidation or corrosion. Zinc is more reactive than iron, and hence when oxygen or water will have to prefer choosing the reaction with zinc or iron, they would preferably choose zinc, because zinc will get oxidized and will save rest of the metal from corrosion. Next is greasing and oiling. Greasing and oiling of the metal basically cuts the direct contact from water and oxygen. When it cuts the direct contact from oxygen, water and other acidic gases, they will not come in contact with the metal directly and hence will not be able to react. Same is the case for the painting also. So painting also cuts the direct contact of your metal with oxygen or water or acidic gases. So hence the metal piece do not get affected by the moisture present around or oxygen present around or acidic gases present around. So understand one thing which is very important whenever we are talking about rusting. Rusting is specifically in the presence of oxygen and moisture both. It's not or. It's not only oxygen is affecting iron or only water is affecting iron. Both should be present for rusting to happen. Similarly, when you will refer the other reactions what I have mentioned both the conditions what are required for reaction to happen. So basically carbon dioxide and water for copper. Similarly, your O2 and H2S for silver. So all these combinations are required. If you have only one out of the other things which are required, then the rusting or corrosion will not take place. Okay, so there are some cases when they give you a question also that your iron nail is dipped into the water completely. Okay, one is kept in open. Okay, but the lid is closed, basically no moisture, only air. Okay, and the other is the nail is half dipped into the water and then in contact with the air also. Where will you see the rusting happening? So rusting will happen in the tumbler where your nail is in contact with water as well as air or oxygen, or you can say the iron piece which is in contact with the moisture plus oxygen, that nail only will get corroded. The one which is completely dipped into the water will not get corroded at all because there is no oxygen around. Okay, though there is obviously we can talk about it that there is some dissolved oxygen also in the water, so that is a different scenario altogether. So assume that there is no dissolved oxygen and hence only water is present, so it will not corrode your iron piece. Now the last way how we can protect is electroplating of the iron. Electroplating is nothing else but the similar thing as the galvanization. So here we have specifically spoken about the zinc. So when we are talking about electroplating is the same concept as galvanization. Only difference is in the galvanization we are specifically talking about zinc, and in the electroplating we are talking about all those elements or all those metals which are better in reactivity as compared to iron. So we plate our iron material with those metals, and those metals get reacted with oxygen and moisture rather than the iron under those layers. Okay, and hence the iron gets saved, but the top layer of those metals get oxidized. Not always they get corroded. So basically sometimes those oxides are stable, sometimes those oxides are not stable. For example, if I talk about aluminium coating on zinc, aluminium oxide is quite a stable oxide. It doesn't make the metal weaker. So if I'm coating my zinc with the aluminium on the top, or I'm doing electroplating of aluminium on iron, aluminium will get oxidized and then will form a stable oxide and will stop further oxidation of iron or further rusting of iron. Neither that coating will make iron weaker nor the aluminium layer itself weaker. Okay, so not always the oxides are weaker than their respective metals. There are few, and in the case where the oxides are weaker than their respective metals, they are basically considered as corroded metal, or when the moisture and oxygen or acids attack and they form certain kind of compounds which are weaker than the metals, then we say the metal is corroded. Okay, so these are the ways how you can protect your metal from rusting. Next, we'll talk about the next application of oxidation and reduction, and that is rancidity.
Topic: rancidity. Why is a bag of chips half full? Looks like you don't believe me. Open the bag. See, I told you. The bag of chips is indeed half full. Why is that so? It is mainly because of a concept called rancidity. When food becomes rancid, it develops an unpleasant smell and taste, and it becomes unsafe for consumption. Rancidity generally refers to a condition where the fats and oils present in food get oxidized, resulting in food spoilage. Since the chips contain fats and oils, they are likely to get rancid. Therefore, to prevent this, nitrogen gas is flushed into bags of chips by manufacturers. But why nitrogen? Nitrogen does not react with fats and oils. As a result, rancidity does not take place. Moreover, a gas in the bag serves as a cushioning agent and prevents the chips from crumbling. That is why the bag of chips is only filled till half.